So good morning, everyone. See, as all of you must be aware, today this weekend your syllabus includes dipole moment and related topic. So I thought we'll revise this topic today. We'll go through dipole, what dipole is, what dipole moment is, what the forces which act on the dipole, giving rise to torque, and its potential energy. So it's kind of revision of what we have done with an eye on the weekend exam. Okay, let's get started. See, all of you, I think this part, I hope all are clear. Any current carrying loop is equivalent to a dipole moment. Its magnitude is equal to current into area multiplied by number of loops, and direction is given by right hand thumb rule. So again, when look at this figure, I hope all of you can spot if it is square loop of side L carrying current I, it has n turns, and we see a different orientation. So in each case, can we find the magnetic dipole moment? More importantly is direction. First case here, what is the direction here? How do you find direction? Magnitude is simple. Magnitude is number of turns into current into area. So magnitude of dipole moment M, that is simple. That would be equal to what? That magnitude of mobile dipole moment will be equal to N into NIA, which is NIL square. But what is the direction in this particular case? If you look at right hand thumb rule, if you curl your fingers in this direction, thumb will point into the plane of the figure, and which would be minus I cap. So direction in this particular case, direction is this one, and direction is equal to minus I cap. I hope all of you can easily spot. Similarly, if we have done through, we'll do a little bit more detail. This figure, as we go along, all of you should try and do in your mind, what is the direction or dipole moment if I curl my fingers along this path. So if my fingers are curling, right hand fingers, if they're curling like this, which direction would my thumb point? I think all of you can easily notice, if you curl your fingers in the direction, thumb will point in the downward direction. If thumb is pointing in the downward direction, what are the downward direction indicate? Downward direction indicates minus K cap. Minus K cap is the direction. Magnitude is simple, we are all familiar with. Okay. And another way to think of, in this particular case, loop is placed in XY plane. Hence, magnetic dipole moment would be perpendicular to plane in which loop is placed, which is perpendicular to XY plane. So it could be either plus K cap or minus K cap, and direction we can find out using right hand thumb rule. So again, this particular case, let's curl our fingers. Which direction? If your fingers are curling like this, right hand fingers curling in this direction, which direction does the thumb point? In this case also, I hope all of you can easily spot the thumb will point in this particular direction. And that would give the direction of dipole moment, but equal to minus J cap. Okay, so that's how we can find out. And many times what we do it makes it much easy to understand if we replace the loop with an arrow indicating the direction of the dipole moment, and that makes it easy to find angles and all. So can we indicate the direction of dipole moment in each case? This is the direction of dipole moment in the first case, minus I cap. This is the direction of dipole moment, minus K cap, and this is the direction of dipole moment. So we can replace this loop with an arrow if you think that simplifies your understanding. Okay, and something like this. Suppose a square, again current is I, and a square loop. Again, the sides are L and L. Can we find the dipole moment in form of unit vectors? So all of you give a try. So how to find out direction of dipole moment, and the current is I in the direction indicated. So what you understand here, yeah, finding magnitude is simple. Finding magnitude is simple. That would be if number of turns are N and IL square. That magnitude is okay. How do you find direction here? So even if I use right hand thumb rule also, it creates some confusion. So another way of thinking of direction of dipole moment would be if this entire loop is placed in, if it is not rotated by 30 degrees. Suppose this is one, this one has been, you can think of it, it has been rotated by 30 degrees. So if we take its position before it was rotated, it was in YZ plane. So when it was in YZ plane, what are the direction of magnetic dipole moment? So when this loop is rotated, the magnetic dipole moment also will rotate. So that's the way we can think of. We can find the magnetic dipole moment direction when it was in easier position, and then see what the change in direction of dipole moment is. So let's look at initially it is in YZ plane and then rotated about Z axis by 30 degree. That's how we can interpret this figure. It is placed in YZ plane and then rotated about which axis it is rotated about? It's rotated about Z axis. By how much? By 30 degree. So when it is in YZ plane, that is simple. If it is in YZ plane, I can find if I curl my fingers, and my fingers will point into the plane of figure, which is minus I cap. So what are the initial direction? Initial direction of dipole moment was something like this. This was the direction when it was placed in which case it was placed in YZ plane. Now it is rotated about Z axis. By which direction it is rotated in this fashion. So what will happen? Even the magnetic dipole moment vector also will rotate by 30 degree along with respect to Z axis. So earlier it was along this direction. It will end up making an angle of minus 30 degree with negative x axis. So dipole moment vector initially along minus x axis. When it is rotated by 30 degree about Z axis, dipole vector will make 30 degree angle with minus x axis, or if I can say other way around, it will make an angle of 150 degree with x axis. That's the direction. So what I need to do, if I have to write moment, how do I write the magnetic dipole moment in unit vector form? I can write this magnitude multiplied by unit vector into unit vector. So what is the unit vector in that direction? There are a couple of ways of doing it. See, I think one I mentioned earlier, which I find is quite easy way. If any vector lies in say xy plane, any vector which is lying in xy plane, if I take a unit vector which is in xy plane, which is the case here. So if I have a unit vector, so if I take if I take a unit vector which is making an angle theta with the x-axis. If this unit vector, this length is 1. So can I write this unit vector in form of I cap, j cap based on this orientation theta? Yes, x component will be equal to cos theta and y component will be equal to sin theta. So any unit vector which makes an angle theta in which direction? In anti-clockwise direction towards y-axis can be written as cos theta I cap plus sin theta j cap. So if I use this particular convention here, so again I look at what is the theta here, what is the angle this vector makes with the positive x-axis. I find this is making an angle of 150 degree. So what is the unit vector here? So if I had to look at unit vector, I could have written this unit vector similar way. I would written in place of theta, I have written 150 degree. So unit vector will be equal to cos 150 I cap plus sin 150 j cap. And what is cos 150? Cos 150 is equal to minus cos 30 I cap plus this is 180 minus theta is equal to sin theta sin 30 j cap. That's one way you can do it. Other way you can take, okay, this is vector which is making an angle 30 degree. I can take its component. If this angle is 30, its component along negative x-axis will be equal to cos theta but minus sin, and y-axis sin theta. Both ways you can do. You can use this by convention also, finding angle with respect to x-axis and find unit vector, or other way around. So do we find what is m equal to? Either I could have written as m cos 150 I cap plus sin 150 j cap, or I could have formed the components here and you can find the magnetic dipole moment in vector form. Okay, and we have done something like this also when a loop is not lying in a plane. So I'll just quickly kind of review the same. So if a current carrying loop is not in one plane, so and here, so this is how the loop is, the current is flowing like this. So what we do here, whenever it is not lying in a plane, we convert into two loops by introducing equal and opposite current along the common boundary. So one current element like this, another current element, same position. So equal and opposite current, they'll cancel out each other. This becomes one loop. In a one plane, this also becomes another loop. So independently, we find the magnetic dipole moment of each loop, and resultant, since dipole moment is a vector, resultant will be a vector sum. And that's the idea behind it, to form planar loop by adding equal and opposite current on the boundary of the loop. The resultant moment is vector sum of the moment for each planar dipole moment. So something like this we can visualize. So it is this what will the direction? You seen earlier also. This will have direction along this direction. This will be the direction of first magnetic dipole moment vector. If I take this loop lying in the vertical plane, and similarly, if we take another one which is lying in the horizontal plane, again, if I use the right hand thumb rule, it is pointing in the downward direction. So magnitude IL square. And so what is the resultant dipole moment? Resultant dipole, this is the value of resultant dipole moment. Okay. So I hope all are clear about this point. Okay. So let's move on to, so basically, and the same thing we can do for something to semicircular loop and any other shape. We also did something which was lying in 3 different planes on sides of a cube. I hope you recall that question as well. Okay, if I add one more question here, what if additional question I add here? What would be the direction of magnetic field at this point here? Suppose this point is given. Can we find the direction of magnetic field? Only the direction, not the magnitude. So think for a minute, how do you find direction of magnetic field at that particular point? I hope all are clear. The direction of magnetic field on the dipole, axis of dipole, it doesn't matter which side the point lies on. The direction of field is same as the direction of dipole vector. So if you have to find the direction of, if I have to find what is the unit vector along the direction of magnetic field at this point, the unit vector will be same as, I could write as this vector. What is this vector? This vector is equal to minus, unit vector is what? J cap plus k cap. If you have to write the unit vector divided by root 2. Thus the direction of field at this particular point. Okay, and one more variety of the question is, if a charge is uniformly distributed over a surface of a thin disk of radius r, what is the magnetic moment if it is rotated with angular velocity omega about its axis? So in this particular case, we know any orbiting charged particle creates a current and it becomes like a current loop, and it has a magnetic dipole moment. But we, in such case, it is what we do, rather than finding magnetic dipole moment, for similar mass distribution, we find out angular momentum I omega. Why it's easier to find I omega? Because most similar kind of shape, we already have the formula for moment of inertia. So we can easily find I omega. And after finding I omega, we can use this relationship. What is the relationship we use? This L comes equal to 1 by 2 mr square omega. In this particular case, we use this condition, ratio of magnetic dipole moment divided by angular momentum is equal to charge divided by 2m. So we find value of angular momentum. Only condition is same value of omega, same axis of rotation. Distribution of mass has to be similar to distribution of charge. Since the charge is distributed uniformly over the surface of a thin disk, we take mass m distributed uniformly over a disk of radius r, same radius. And then we can calculate L, and we substitute L here, easily we can find. And to remember the formula also, this term is dependent on charge, this term is dependent on mass. So quite logically, what we find here, the charge term comes in the numerator, and mass term comes in the denominator. Okay, this is how we can find. That's about angular momentum. Now let's come to understanding of torque. So let's take a case here. This is a rectangular loop. Side AB is equal to M, and other side, this side is equal to BC is equal to N. It is carrying current I as shown. It is placed in XY plane. If there's a uniform magnetic field given by this, is the field uniform? If these two values are constant, field is uniform. It is independent of position. It does not depend on the coordinate or does not depend on position. If this field existed, can we mark the forces on 4 sides and the resulting torque? Okay. So this is what, again, can we mark the forces on the 4 sides? And see, actually what happens, force act and force will result into torque. So can we mark forces? To mark forces this time, let's use slightly different approach. What we'll do here, this magnetic field, see, if you look at it, has a, what is the, how is this field here? Field has a component along this direction. It also has a field along, component along Z direction. So field has component in the plane of the loop, and field also has a component perpendicular to the plane of the loop. To understand this better, what we'll do this time, we'll calculate force due to one component at a time. Perhaps that gives a slightly different perspective and different understanding. Okay, so consider forces due to only y component. The y component is where? Y component is lying in the plane of the loop. So which is the direction of field? Yes, field is acting along this direction, by. What will the direction of forces and magnitude of forces due to this? Okay, so if you notice there, it has 4 sides. Out of these 4 sides, 2 sides will not experience any force. Which 2 sides will not experience force? The sides which have current either in the same direction as the field or opposite. So you can easily notice these 2 sides will not experience any force. How about side AD and BC? How do you find direction of force here? Either I can use right hand. So what is the direction of current? This is the direction of current. So one way of, if this is direction of current, one way I can think of, this is my L vector direction. This is L vector and this is B vector. L cross B, I can find out using right hand thumb rule. Those who are not comfortable using right hand thumb rule, I can also find direction by taking a unit vector in the direction of current or direction of L vector. What is the direction of L vector here? It is going along negative x-axis. So this direction is actually equal to minus I cap, and B direction is J cap. So that way also I can find direction of force on side AD. And if whatever direction of force acts on side AD, BC will act equal and opposite. That's why the net force will come 0. So that's how we can write. This is B direction. Let's do step by step what we are saying. So all of you try and do in your mind as well. So no force on 2 sides, and 2 other sides forces will be vertical and opposite. If you have to find direction in AD, I could have taken the direction as L vector minus I cap cross J cap, which comes equal to minus K cap. So I could have found the direction of force without even using right hand thumb rule. So which direction is the force acting on AD? In the downward direction. In case of BC, it will act in the upward direction. This is how the forces are acting. So what happens? So what we understand here, the net forces are 0, but this force are acting, and this force will create a torque. It will create a torque which is independent of choice of axis, which is called couple. Equal and opposite forces create a couple. So we understand this is the effect of Y component of field. This is the nature of forces it is producing, and it creates a couple. And couple also, can we calculate the value of couple? So if it is in free space, what will happen if forces are acting in this fashion? If it is kept in free space, this force is trying to push it down. This force is trying to push it up. So what will happen to this coil here? It will tend to rotate. And if I stand here, how would I see it rotating? Would it appear clockwise and anti-clockwise? It will appear to be rotating in an anti-clockwise direction. And this is sense of torque. What is this torque? Can I define the direction? If I curl my fingers along the direction of torque, my fingers are pointing towards plus x-axis. So I cap will be the direction of torque. So in free space, it will rotate about center mass. Okay, which axis it will rotate about? If it is kept in the free space, it will rotate about this axis. This side going down and this side going up. And if I have to define axis of rotation, or if I have to define torque value, or what is the value of omega it will acquire after a small time interval, it will be I cap. Okay, it will tend to rotate like this. But if it is placed on a horizontal surface, will it behave in the same way? If it is placed on the horizontal surface, behavior will be slightly different. If it is placed on the horizontal surface, so suppose XY plane is a horizontal table it is placed on. This force is trying to push it down, but if it is kept on the floor, this side cannot go down. But this force is pushing it up. If force is large enough, what will happen? This side will get lifted up. So if it is kept on a horizontal surface, it will tend to rotate about side AD. I hope all are clear. So it will tend to rotate about side AD. That's how we can understand. So far what we have done only the effect of Y component. And do we understand how do we get the direction of tau? How do we get the direction of tau? How did we get this direction of tau here? So here, if I look at the figure, I didn't use any cross product. So direction of torque, if you're marking the forces, we understand which direction of torque is acting, and I find the direction of torque is I cap. There is some other way also, which is M cross B, will come to again later. What are the forces? This force, each force is of magnitude. If this side is N, it is equal to magnitude of force is equal to IN into By, and they are acting perpendicular distance between them is equal to M. And that's what the torque is equal to. If you multiply by M, that becomes torque, which is I into N into M is nothing but magnetic moment. And when we take the direction, that's how it becomes equal to M cross B. So another way to understand that one, and this torque or couple independent of axis due to forces, it will be IN By into M. Okay. And torque is M into By. And if you want to understand direction of torque, one way to understand, we can mark the direction. This is where B vector is, and this is where M vector is. And how what torque will act? Torque acts such that I can take cross product M cross B. So if my fingers are curling from first vector to second vector, thumb will point towards me. Same thing what we have understood from marking the forces also. So I can do that. And what is torque trying to do? Torque is trying to rotate M in such a way that it tends to get aligned with B vector. So torque will act so as to align magnetic dipole vector with magnetic field vector along the shortest path. So it will rotate in the plane which is containing M vector and B vector. In this particular case, both two vectors are contained in which plane? Plane parallel to YZ plane. So it will rotate in YZ plane. So, so torque will be perpendicular to YZ plane, which is plus I cap in this particular case. Okay. Now we have done one part. Let's do the second part. What is the first part? We have done the effect of a field which is lying in the plane of the loop. It creates a torque. How it creates torque, we have understood, hopefully. Now we'll understand the second component. Which component? No, K component is perpendicular to plane of loop. Consider forces due to Z component, perpendicular to plane of the loop. This is how the Z component is. This BZ is in the along Z direction. So since it is in vertical direction, forces will lie in horizontal plane. Forces will lie in the horizontal plane. It will lie in the plane of the loop. Okay, so I hope you all have understood, but force is perpendicular to a magnetic field as well. If magnetic field is along Z direction, all forces will lie in XY plane. And since loop also lies in XY plane, it means forces will lie in the plane of loop. So when forces lie in the plane of loop, all forces are either all in or all are out. So if we find direction of force in one side, we can easily interpret direction of forces in other sides of the loop also. Let's try and understand which direction the force will act on side AB. Side AB, what is L vector here? So side AB, I can use vector property as well to find direction. Side AB, L vector is along minus I cap, and B vector is K cap. So direction of force inside DA will be along minus I cap cross K cap. That's the direction of force. On side AB, force on side AB. Okay, sorry, this I not written properly. Force on direction side AB will be equal to AB is equal to minus I cap. So, sorry, AB is okay. Just a second. I think this side first I written okay, not DA. This side this time calculated force on side AB. Which direction the force will act on side AB? AB is along J cap. This is the direction of L vector, and this direction of B vector. So J cross K, it is I cap. I cap is which direction? This is the direction in which force will act on AB. It is acting inward. So one force is inward, all forces are in. This is how the forces will act, and no torque will act, no net force will act. So what we understood, if there is a magnetic field which has component in the plane of dipole moment as well as perpendicular, the component of magnetic field which is perpendicular will not create any torque. Torque gets created only by the component of field which lies in the plane of the dipole or plane of the current carrying loop. That's how we can understand. So this component is not creating, it is only trying to shrink it. So effect of these forces will try be equivalent to creating a compressive force. If this is kind of rod or this is wire element, it will create a kind of compressive force. Had it been circular, we could have calculated that force also. It tries to compress the loop here, and hence it will create compressive forces. Okay. Coupled due to force is 0. Or due to field perpendicular to the plane of loop is 0. I hope this is another way to analyze effect of magnetic field on a current carrying loop or effect of magnetic field on a magnetic dipole. This time we are analyzed with two components, one in the plane of loop, other perpendicular. So which one creates torque? The one which is lying in the plane of the loop. Okay. So in this particular case, why torque is not there? Again, if you mark the direction of dipole moment vector, this is the direction of dipole moment vector, and this is the value of direction of B. Angle between them is 180, and no torque is acting. Okay. So torque under dipole, to understand potential energy. Potential energy is actually work done by the magnetic forces, but magnetic forces, work done by magnetic forces are much easier to calculate. So compared to work done by force, it is much easier to calculate work done by torque or work done by couple. So we write torque under dipole is equal to minus is m cross b. Why do we write a minus sign here? Do we recall why do we write a minus sign here? Because if m and b are initially, suppose they are in the same direction. Okay, this direction m and b. Okay, at that time there's no torque acting. If I give a angular displacement to theta m, if I give angular displacement theta to m, so that it starts making angle theta with b vector. If I give a displacement, angular displacement in anti-clockwise direction, torque will start acting in the clockwise direction. It will try to bring it back. So torque is always opposite to theta. So when we are writing here, that's why I written minus mb sine theta, because it's opposite to direction of angular displacement. So change in potential energy is equal to negative of work done by conservative forces. In this case, I'm writing as negative of work done by conservative torque. Okay, negative of this. And if you recall, I am not going to derivation. So very simple. So we assume, in this case, we take the reference point or angle at which potential energy is 0 is when angle is 90 degree. So when they are mutually perpendicular, that's the time we take the reference as 0. Because that only leads to a simpler form, which simpler form is potential energy is equal to minus bar dot b bar. Okay, that's the potential energy. And if you recall, it's a negative cost function. It increases continuously from 0 to 180. Potential energy keeps on increasing. And if we simply use this formula, we can find for different angles what the torque will act and what the potential energy will act. So let's try and understand this. I think this potential energy is simply substitution of value of theta. So if I have to calculate what is work done to rotate a magnetic dipole from 0 degree to 60 degree. Work done will be equal to, what is work done? Work done is equal to final potential energy minus the initial potential energy. So when I subtract from this quantity, work done will be this quantity minus this quantity. So this will become plus. The work done to rotate a magnetic dipole by 60 degree will come equal to mb by 2. What is the work done to rotate by 90 degree? In that case, from which position? From initial position of equilibrium, which is 0 degree. The work done to rotate by 90 degree will come 0 minus mb, which will equal to mb. So work done to rotate by 90 degree becomes mb, by 60 degree mb by 2, and by 180 degree it becomes 2 mb. So we need to take the difference. I hope you know how to apply those things. So work done calculation, and we also said at each angle, these two quantities, they have same dimensions. So we can also find the ratio of these two quantities at different angles. So there could be some questions which relate torque as well as potential energy, and not very complicated, simple thing, you can do that. Nice. Now a similar question, now I'm asking a little more. Let's see what this question is stand for. Again, this square loop, current carrying loop, and turns is placed in which orientation? It is placed in YZ plane. Okay, and there's a magnetic field which is a bj cap plus bk cap. Uniform magnetic field exists in the space. Find torque, potential energy of this loop, and maximum kinetic energy it will gain if it is placed in free space. Can we find all three terms? So I give you a couple of minutes for all of you to think, how do you find all three terms? Okay, so finding torque, the way we have found torque. So first thing what should come to our mind, since already given in unit vector form, I need to write torque is equal to m cross p. I need to write m in vector notation, which is easy. I find the direction using right hand thumb rule. And what is potential energy? Potential energy is minus, again, it's a dot product between two vectors.
Yes, B, yeah.
So in this case, is that difficult? Once we have m vector, I will take a dot product. Is the dot vector difficult to find?
No, sir.
No. So let's see one by one. So is that a difficult question to answer? No, it should not be a difficult question. So what will the dot of P be equal to? If I have to write P, how would I write? I'll put a minus sign here. And Ni L square minus I cap dot of
BJ cap plus BK cap.
what does this mean? What is potential energy at this point of time? What is the dot product of these two? Ij also 0, Ik also 0. So what is potential energy? Potential energy is 0. Can we explain logically why potential energy is 0? See, when you look at this, what is the direction of field here? Where does the field lie in? Field lies in YZ plane. How is the field direction? This, if I mark the direction of this magnetic field, field is in this direction. Field is lying in the plane of the coil. When field lies in the plane of coil, angle between m vector and field vector is 90 degree. And we already know potential energy has to be 0 when angle is 90. So P is 0. Now third part, what is the maximum? So kinetic energy it will gain when it placed in free space. And what is the maximum kinetic energy it will gain? Is this K max will be equal to, why it will gain kinetic energy? It will lose potential energy. What is the minimum possible potential energy? See, it is 0. So finally, kinetic energy will become maximum when potential energy becomes minimum. K will be maximum when P is minimum. What is the minimum value of potential energy? Minus MB. Right now it is 0. So from 0 it will drop to minus MB. So what is the loss of potential energy? Loss of potential energy MB. So kinetic energy gained also will be equal to MB. Kinetic energy gained also will be equal to MB. Anvita, are you clear about this point now?
Yes, sir.
When is kinetic energy maximum? When potential energy is minimum. What is the minimum value of potential energy? Not 0. Minimum value of potential energy is equal to minus MB when angle theta is 0. So from 0, so what is the how much loss of potential energy? That will come gain into a kinetic energy. So loss of potential energy, so K will be equal to P final minus P initial. P final is equal to loss, sorry, when I'm writing loss, I will write it P initial minus P final. What is P initial? 0, and P final is minus MB. So what is loss of potential energy? MB, and that will be the gain in kinetic energy. All are clear? Okay. Now this question also I could have to understand. Okay, this is basic part what we have done. Suppose I ask you, suppose you have to visualize about which axis it is placed in free space. Why it will rotate and which axis it will rotate about. Why it will rotate and which axis it will rotate about. Can we figure out? Okay, sorry, I think not written that part. Which axis will rotate about? See, let's look at this. Okay, if you want to examine not in formula, if you want to go a little more detail, let's take the first J component. So let's take effect of field, effect of J component. How the J component? This is how the field is. If field is like this, what are the forces which will act on two sides? This side no force will act, this side no force will act. Which direction force will act on this side? What is direction of current? This is the direction of current. So if I take this side, the direction of force on this side will be in which direction? This is K cap direction. It will be direction of force will be K cap cross J cap. What is K cross J cap? Minus I cap. It means force on this side will be into the plane. It is, so force is pushing this side into pushing in. And what is the direction of force? This will be direction of force on this side. I hope all are understand. So what will happen if only this component is acting? What would happen if it is placed in the space? It will tend to push this side in. It will tend to push it towards us. It will push this side away from us, this towards us. If it is placed in the free space, J component is trying to rotate it like this. Thus, effect of J component. I'm just going in more minute details so that we just get a better understanding. What is the effect of other component? Effect of K component. So now if I take the effect of K component, vertical component, K component. So effect of this direction, this foil is in this direction. Now these two will not experience any force. Force will experience only by these two elements. Let's find out direction of force in this element. This direction is along J cap and this is K cap. The force on this element will be along J cap cross K cap. J cap cross I cap. So the direction of force in this element is like this. And direction of force accordingly here will be like this. So you know how it will rotate. Actually, it will. This is something. If I mark these forces, I think I get an understanding. It will rotate like this. If I take a diagonal, as it is like somebody is pushing these two sides into the plane. And these two sides are being pulled towards me, and these two sides are being pushed away from me. How it will rotate? It will tend to rotate about this axis. And if I mark the direction if I use right hand thumb rule, this side is coming towards me, this is going in. So if I curl my fingers along the direction in which different parts of this will rotate, my thumb will point in the downward direction. This is the direction of torque. Somebody is getting this direction also what I'm saying now. So this is something, see each part, it will tend to go in a circular path, and this is the direction of torque and this is the direction of omega it will acquire. And that is based on my understanding from each taking basically finding out force on each element, how the forces will act and how it will tend to rotate. Same thing I could have done using formula also. Let's see how do we do using formula. How it will rotate. See, as for our understanding, now let's look at this. We are trying to understand if it is placed in free space, how it will tend to rotate, what will be the axis of rotation, and how the torques and all will act. So here, can we mark the direction of field? Yes, field direction is this. This is the direction of field. And what is the direction of dipole moment at the center? Dipole moment in the center is into the plane of paper. So what will happen? The dipole moment which is into the center, it will try to align itself along the direction of B. How it will align itself along direction of B? So this is something it will rotate about this axis, which is perpendicular, and then it will come and align with B. So this is the axis of rotation. This side will move towards us. This side will move away from us. And this will be diagonal will be axis of rotation. And we can do so this. All of you can try and do it for different shapes as well. Okay. Exist. This case also, can we find torque? Once we have found m vector, finding torque and potential energy becomes easy. Similar method, all of you can try. Those are all of you can calculate torque, potential energy, and maximum kinetic energy. For this shape also, because we already found m vector in form of unit vectors. Once we have that one, finding dot product and cross product, all we need to do, we just need to find cross product to find torque. We need to find the dot product to find potential energy, and we need to keep it maximum kinetic energy will be equal to negative value of this maximum kinetic energy. Also, I hope all of you understand how to calculate. Maximum kinetic energy will be equal to loss of P. What is loss of P? Loss of P means initial potential energy mode, P initial minus P final. P final is equal to minus M. So if initial energy is greater than minus MB, there will be always loss of potential energy, which will result in gain in kinetic energy. Okay. This also we can do I think all questions similar way we can solve, and we can get this answer, dipole moment. Okay, let me do one more question. Just read the question carefully before we solve this. So you understand this is a rectangular loop. So one side, by the way, okay, we can take anything. This side, so let's say this side is A, other side is B. It is having current flowing through it. Okay, it is suspended by a string. I think this will take as a midpoint, and from here it is suspended at a point which is vertically above is center of mass. It is center. This is how it is suspended. So this entire rectangular loop, the center of the loop coincides with the origin. In presence of magnetic field, what it is found when you suspend by the string, normally what should happen? The whole plane of the loop should become vertical under gravity. But here what we find, when you suspend here, we find the loop remains horizontal with the string making angle theta with the vertical. So this is an angle theta here. The loop remains horizontal in presence of magnetic field. Can we find what is the minimum strength of magnetic field and direction necessary for this to happen? Mass of the loop is m. These are the sides given. So how do we understand, but how do we analyze? So if we have to look at, if it remains passive, first, if it is suspended by a string, it remains horizontal. This string has to have some tension. So in terms of forces, if I understand, okay, this force is acting, and its weight also will act in the downward direction. So weight also is acting mg here. Now, if it has to remain horizontal, it means, see how, if suppose magnetic field was not there, how could we keep this something like this in horizontal state? I have to apply some force upward direction. So here, force on this element must be acting in which direction? Upward direction. Then only it can remain in rest. Then only it can, I hope it makes sense. So is there something, so force acting on this side, I'm trying to understand what must be the direction of what will keep it horizontal, and using basic laws of motion, can I figure out what would happen here? The force must be acting upwards. If force is acting upward, what must be the direction of magnetic field so that it creates a force in this element in the upward direction? What you're saying here, what is L vector? L vector is along minus I cap. Multiply with direction of force this is leading to a force along K cap direction. So what should be the direction of magnetic field here? It is possible cases are what? It could be either J or minus J. If it is J, it will not come minus. If it is minus J cap, it will lead to, cross product will lead to K cap. So what has to be direction of magnetic field? Magnetic field has to be in this direction. But it can have also I component. But if it has an I component, that will not create a torque. That will not be the minimum field. The field will be minimum when it is it creates a yeah. If it has other components, it will not remain minimum. So this creates a force like this, and if field is like this, force on these two elements will be 0, 0. So one way I can solve this question. Okay, so these are forces here. So can this mg is acting here? This no force is acting, no force is acting. Here what force will act? Length is a. So force acting, what will the magnetic force here? Can we tell this force equal to? If current is I, force will be I, length of the side is a into b. That's the magnetic field. This is a force which is acting. Okay, can I relate this force to mg, and can we apply condition of rotational equilibrium? See, if a t is passing through this point, without calculating t, if I take torque about this point to be 0, it becomes easy. This will not have any torque. So t will not come into equation. So let me call this point as p. To find phi, I take the torque about point p to be 0. So how do you solve? Torque about point p is 0. If I take torque about p is 0, mg will have a torque equal to mg into b by 2. And I'm just equating the magnitude. Directions are already opposite. It has to be equal to fb into b. Or what does it mean? Fb has to be equal to mg by 2. This I'm solving without, okay, this f by 2. So what is fb? Fb is equal to I into a into b, has to be equal to mg by 2, or b is equal to mg by ia. Same thing I could have done. Okay. What is the other way we could have done solve this question? Other way of solving this question is, you see, how do other way we solve? Other way we solve this question is, okay, what is the torque due to magnetism? I have done using force now. Using torque, how would I have done? What will the torque if B is like this? Torque will be equal to M into B. What is M equal to? IAB into B. This is torque. And which direction the torque acting? Of course, the torque has to act, magnetic field torque has to act in anti-clockwise direction. And this torque is, since it is created by couple, is independent of choice of axis. In that case, I'm not taking net force. So again, in this case also, if I take, if this is the torque acting, I take the net torque about point to be 0. If I take net torque about point to be 0, I would have written this one. This, I would have taken this as an anti-clockwise torque, which is MB minus torque due to mg into b by 2 is equal to 0. Both gives me the same result, but whichever we find easier to understand, this is something using force, because I can do if it is a rectangular surface. If it is a rectangle, I could have done like this. But what happens if I replace the whole thing with a circle? Suppose not a rectangle, if it was whole thing was a circle. If circular loop is carrying current and is kept held in a horizontal plane. Okay, so yes. Okay, just let